Okay, so thank you so much for the introduction. I'm really happy to give this seminar and to share all these recent works we did about energy efficient AI. So I think this is new format for these seminars. So please, if there is any technical glitch, if you cannot hear well or something like this, do not hesitate to interrupt me and to scream, and we will fix it. So yes, my name is Damien Carrios. I work at the Centre de Neurosciences et Nanotechnologie, which is a joint lab operated by the university and CNRS, and we are on the plateau, very close to AgroParisTech and Telecom ParisTech. But before really jumping into the topic, let me introduce a little the context of this work. So I think you are all aware that AI, artificial intelligence, has made tremendous progress in recent years. So I think this was all over the press. This is a new AI that was released this year, and it's an AI you can just say what you want. So for example, you can ask the AI a photo of a confused grizzly bear in a calculus class, and in only a few seconds, the AI will produce an image like this, which is basically exactly what you asked, with almost photorealistic quality. You can even ask for kind of crazy stuff like teddy bears working on a new AI research on the moon in the 80s, and you get something like this, which is actually quite exactly what you wanted. The teddy bears are on the moon. They are working on computers because it's supposed to be AI research, and these computers kind of look computers from the 80s. These kind of things, even a few years ago, would have been unthinkable. The progress of AI has been really amazing. And AI is not only about producing funny images. In recent years, AI has also become a lot better at understanding human language. And for example, this year, we had this really big milestone, which is an AI from Google that can actually answer questions, require reasoning, or even something that's really difficult, explaining human jokes. So here you have an example where somebody says, I was going to fly to visit my family on April 6th. My mom said, oh, great, that's poetry reading in that night. So now I'm flying on April 7th. And then you can see the AI is able to explain the subtext of this. Not literally what is said, but what the person really means. And that's also something that was extremely hard for AI until very recently. Also, probably most importantly, now AI is widely applied for medical research. And actually, I think all the medical doctors I know at hospitals currently are applying AI to their data to really help them diagnose and really help people. So all this is wonderful, but there are things about AI that are less discussed. And indeed, one of the biggest problems of AI is actually a problem of energy. Because a sad reality of AI is that it requires a lot of energy. And I'm going to give just a few examples. So for example, I'm sure you have all seen these self-driving cars. Actually, there are some of them driving on our campus. And these self-driving cars, they actually use big computers. And the AI of the car actually uses a power consumption of 2000 watts, just for the AI. And if you compare with the power consumption of our brain, which we use when we drive, the power consumption of our entire brain is only 20 watts. And only a small portion of this 20 watts is really used for driving. A lot of it is operating our most basic operations. So you can see this difference that already tells you there is something different between our brain and AI. And our brain seems able to do complicated stuff with a lot less energy. And the difference is even more striking when we talk about actually training the AI. That's really creating the AI. So if we come back to this model I just showed by Google that can understand human language, Google was actually very honest about that. And they told that they actually use 3.5 gigawatt-hour of energy, of electricity, to train this model. And to be honest, that's really the time it worked. But before that, they needed to do a lot of research, and basically they had to spend this electricity many, many times. Literally, they spent millions of dollars of electricity to create this AI. And to give you an idea, 3.5 gigawatt hours of electricity corresponds to the energy consumed by a human brain during 20,000 years. And obviously, it takes way less time for a human to learn human language. So that's also an illustration that there is something deeply inefficient about how AI works and much more efficient about how our brain works. And because AI is starting to become so important in our lives, it's really important to fix this AI inefficiency, or it would be really bad for our planet. And so this will be the outline of my presentation. So first, we are going to spend a little time to understand why computers use more energy than the brain for this type of very intelligent tasks. And based on that, that will allow us to switch to modern research that is trying to fix this problem. So we are going to see that we can use electronic devices that are called Memristors. And I'm going to show how we can use these new devices to make energy efficient AI. And then I'm going to show some of our really crazy research where you use the imperfection of this device to actually be able to learn AI, because as I told you, learning AI is really the biggest problem in terms of energy consumption. So we have a quite full program, but let's start by this very fundamental question. So currently, all these really impressive AI that you see in the news, they are based on a type of algorithm that is called neural network. And quite interestingly, these neural networks are in fact mathematically quite simple. So this is a schematic, very cartoonish schematic of a neural network. So let's imagine the neural network has been tasked to recognize images of cats. So the way it works is that you have neurons, so these are the circles, that are connected by synapses. And on one side, the neurons present the input, and then you progressively calculate the value of these neurons until the output. And the idea of how a neural network works is that if the image is a cat, the output will be a 1. And if the input is not a cat, the output will be 0. And these neurons, they are calculated with this equation. So you can see the value of a neuron is actually the sum of the value of the neuron to which the neuron is connected, weighted by some values. And these values are the values of the synapses. They are called the synaptic weight. And then you apply a nonlinear function that can be actually very simple. And basically, that's it. That's only the equation of a neural network. So you have to calculate these weighted sums, so that's product and sum, apply a simple nonlinear function, and at the end, you'll get your answer. It's actually quite fascinating that modern AI is based on very simple mathematics. But of course, it's not easy to get it working. And to get it working, what is really important is to find the values of the synapses that connect the neurons. So what makes neural networks intelligent is really not complicated equations. It's just that you are able to find these correct weight values. And of course, here I made a very cartoonish neural network that is very small, but for modern applications, neural networks are actually very big. They can have millions or billions of synapses. And to find the correct synaptic values, we do what is called training process, is that we literally use billions of examples and we train the neural network based on the examples to find the correct synaptic weights so that the neural networks can solve these examples. And when you have finished this process, you get a neural network that can do these intelligent tasks based on newer images. So now you can wonder, because the operation of a neural network is so simple, why does it consume so much energy? And the reason is actually that computers are just not optimized for doing this type of task. Because you see, neural network, you don't have that much mathematics to do. It's very simple equations. But on the other hand, you have many parameters, possibly billions of synapses and neurons, and you have to store the value of these synapses. And unfortunately, computers are much more efficient at doing arithmetics than actually accessing data. That's because in a computer, the location where mathematics is done, where arithmetics is done, is actually separate from where data is stored. And if you look at these numbers that come from a modern computer, you can see how bad it is. If you take as a unit the energy a computer needs for adding two numbers, and you compare with the energy that is used by the computer to actually access the data that you want to add. You can see that if the data is stored on the same chip as where the arithmetics is done, it takes 60 times more energy. And if the data is stored in an external chip, as is the case, for example, in the main memory of a computer, it actually takes 3,000 times more energy to access the data than to actually do an addition on the data. So you can guess for AI where the problem is, because in AI, we don't do that much arithmetics, but we have a lot of data, so we need to access the memory a lot. So computers are actually deeply inefficient to do AI. And what's very interesting is that our brain functions very differently. In our brain, basically, we don't have to spend, so yes, there is a slight issue with my slide. In the brain, we don't have to spend the energy to access data. We only spend the energy to add the data. And the reason is that in biology, logic and memory are actually co-located. The brain is actually a neural network. It functions with neurons and synapses, but they are organized differently than in a computer. In the brain, so you have your neurons that kind of does arithmetics, and you have synapses that connect the neurons, but the synapses are really, I mean, if you have a synapse that connects two neurons, the synapses is really between the two neurons. It's not like in the computer where you would like have all the neurons on one side on the computer and all the synapses very far away. And so when a neuron needs to access a synapse, data needs to travel very far away. In the brain, synapses are exactly right where you need them. And so you don't have energy cost to actually access the synapse. So that's a lot more efficient. And as a matter of fact, in the brain, you have 10,000 times more synapses than neurons. So the way I think about the brain is really some kind of gigantic memory where you have some computation in the middle that happens. So we say brain does in-memory computing. And that's our major inspiration. But that's actually not the only reason why brain is so energy efficient. In fact, brain computes a lot less accurately than computers. In fact, the brain computes with electric devices that are called ion channels and the synapses we have been talking about. And these devices, by the standard of electronics, are actually really bad. They are very slow, they are very noisy, they are very variable. All of them are quite different. This means that the arithmetic operations that the brain is doing are actually quite approximate. Very imprecise. So the new operations that neurons do are very imprecise, but despite that, brain managed to be powerful. Computers, on the other hand, compute using extremely precise arithmetics with 64 bits or 32 bits number, and it's always accurate. The computers never do mistake. So that's amazing that computers are so precise and so accurate, but this has a big cost. Big and doing accurate operation is very costly, whereas brain does approximate operations, which is a lot less costly. And very interestingly, we have discovered that artificial intelligence does not require this very accurate computation. So this is a historic example. A neural network was tasked to recognize images, and it had been trained with floating point 32 bits number, which is what you would normally do. And then the researchers redid the neural network, but with a lot less accurate operations. So, for example, they operated the neural network with integer 16 bits, 8 bits, or even 4 bits. And if you have done some computer, you realize 4-bit computation is very, very, very imprecise. And what is plotted here is the error rate of the neural network. So you can see with very precise operation, it makes 7% error. And when you make operation 16-bit or 8 bits, it's still 7% error. And if you make 4-bit, it's actually 8% error. It's really not that bad. So that means the strategy of the brain to do arithmetics that is very imprecise, we can actually do it in machine learning as well and get a lot more energy efficient AI. And so the two ideas for making AI more energy efficient is that we should really bring logic and memory closer and compute less precisely. And even a few years ago, these ideas sounded crazy. I mean, why would you compute less precisely if you can compute more precisely? But now these ideas have been widely accepted. So for example, industry already develops new computers that are only for AI. So Google, for example, has developed these tensor processing units, and these are now quite mature circuits. As a matter of fact, my new phone has one in it to do AI with less energy consumption. But actually, academic researchers, we think we can do a lot further. And actually, we think we can, so these Google chips, they bring logic and memory closer. But what we think is that we can actually do like the brain does, totally merge logic and memory. And instead of just computing less precisely, we can really do like the brain does, compute using the physics of our electric devices. And so that's what I'm going to show you in our talk, the research that we do to make AI way more energy efficient. So the first part of my talk is about this energy efficient AI with Memristors. So what do I mean? So if we want to make AI like the brains, we need to make some kind of artificial neurons and artificial synapses and connect them in the same way the brain does. In fact, doing artificial neurons is not that hard. You can use traditional electronics that is based on CMOS technology, that means transistors, and you can do things that are quite similar to the neurons we need to do machine learning. What is really hard is to do synapses, because synapses have memory, they store a synaptic weight, and yes, memory is hard. In fact, when you use conventional technology, you need to use a type of memory that is called static RAM, so that's this circuit. And you can see, even to store a single bit of information, so that's just 0 or 1, you need these 6 transistors, and they are wired in a very complicated way. So this circuit actually takes a lot of space. And so that means that it's really problematic. If you want to merge logic and memory, that means you need to use this circuit as memory. And so that because it's so big, you cannot have a lot. And so that's why actually in computers, we really separate main memory from the processor, because then we can use another technology for the main memory that is a lot smaller and a lot cheaper. So if we want to do like the brain, integrate great logic and memory, we need a new technology to do our memory and our synapses. And the really good news is that this technology now exists. And it is called Memristor, or in industry, it's rather called RRAM, which means resistive random access memory. And you can see, so this is fabricated by our partners in Grenoble at CA Leti, and you can see electron microscopy of a computer chip that has this technology. So the transistors are here, so that's normal electronics, and here on top you have wires that allow connecting the transistor together, and then even on top you have this Memristor, this new technology that is based on hafnium oxide. So it's really a nano device. I mean, this thing can be typically 100 nanometer diameter. And these devices can really be thought as some kind of artificial synapse. So the way it works, you can see, I have a cartoon here. You have bottom electrode, top electrode, and in between this hafnium oxide, which is called resistive switching material. So it's a little like a synapse. It has two sides. And the idea of Memristor is that it's actually a quite unstable material. So if you apply a very high voltage between the two electrodes, you can actually move atoms inside the material. And when you move these atoms, this will create this type of filaments that are conductive. And once you have created these filaments, that means electricity can flow between the two electrodes, and so your device becomes low resistance. But once the atoms have moved, they will stay the way they are. So you have really programmed your device, and it will remain low resistance. On the other hand, if you apply a very high voltage in the other direction, you can see you can actually move the atoms the other direction and remove your filaments. And when there is no filament anymore, your device is in high resistance. It doesn't conduct electricity well. And same, if you stop applying the high voltage, the atoms are going to stay the way they are, and so your device is going to remain in high resistance. So you can really, using high voltage, program your device either in low resistance or in high resistance. And when you use low voltage, you can just see what the resistance is. So it's very similar to a synapse, because synapse, you see, if it has a strong synaptic weight, it will transmit information well. So it's really like it's low resistance. On the other hand, if a synapse has a small synaptic weight, it will not transmit information well. So it's like the Memristor that has high resistance. So we can really use these devices as artificial synapse. And when you do that, things turn out great. Because let's look at this circuit. So this is a cartoon. Let's imagine I have fabricated many memristors and I have organized them in an array like this. And in my array, I have horizontal wires and vertical wires. And at the intersection of horizontal and vertical wires, I put a memristor. And let's imagine you apply voltages on all the horizontal wires. When you have a voltage that is applied on a memristor, you will have a current that flows, and due to Ohm's law, this current is going to be the voltage multiplied by the conductance of the memristor. So the conductance is the inverse of the resistance, 1/R, expressed in Siemens. And so you have a current here and so this conductance, I'm going to call it W, like a weight. So in my device here, I have a current that is the conductance of this memristor multiplied by this voltage. In this memristor, I have a current that is the conductance of this memristor multiplied by this voltage, etc. And you have all these currents that go onto this vertical wire. And you know, through Kirchhoff's current law, so la loi des nœuds in French, that these currents will sum. And the current that arrives here is really the sum of the conductance of all these memristors multiplied by all these voltages. And now you can guess why I decided to call the conductance of the memristor W and not G, because this is actually exactly the equation of a neural network. So here you can see the magic that happens. When you organize memristor as an array, and you just apply voltages on the horizontal wire, what you get naturally is the equation of a memristor. And you don't need, actually, this happens in analog, so you actually don't need to have all the normal arithmetics you would have in a circuit. And really what happens, which is so important, is that the computation, so the equation of a neural network, happens at the level of the memory. So you don't separate logic and memory. And so as I have said before, you save a lot of energy by doing that. And so it's not exactly like the brain is doing. I mean, the brain is actually not using Kirchhoff's law this way, but you imitate the spirit of how the brain works, which is to associate computation and memory very tightly to save energy. And this is a concept. I mean, it's a concept that was proposed more than 10 years ago. It has taken quite a long time to make it work. But now the technology has really matured and we can actually do that. So here is an example of circuit that we fabricated in collaboration with our partners at Aix-Marseille Université and Leti in Grenoble. So this is actually the full circuit. So to be totally fair with you, the actual fabricated circuit does not look like that. This is a cartoon. When you want to do it fabricated for real, you need to add a lot of transistors, so that's normal electronics, to make it work. So that for the voltage that is applied is the right voltage, so that here you have also a zero voltage, that you can read the current, so that you can really avoid all leakage problem. So this is cartoon. Reality is really hard to do. But we can do the reality. And so we actually fabricated a small neural network with these memristors. And then we programmed we programmed all the memristors, which choose their resistance, so that this neural network would be able to recognize arrhythmia. So that's basically so you present as an input a heartbeat that has been measured on a patient, and the neural network will tell you if it's normal heartbeat or if it's an abnormal heartbeat, that the patient has a heart problem. And we programmed the Memristor, and it worked really well. It was our system was able to recognize heartbeat 95% of the time. Unfortunately, we had a problem is that Memristors are not that stable. And so if we measure again the thing 15 hours later, then depending on the times, it would be able to recognize the heartbeats like between 77 and 87% of the time only. So that's why we did a lot of research, and we found a way to program the Memristor so that they would be a lot more stable. So with our new technique, it's a little more complicated to program the Memristor. You need to try several times. But after that, you can actually program your Memristor. So your system is accurate 95% of the time. And if you take your system again 2 months later, it still is able to recognize. So you basically put it on the shelf, forget about it, and bring it back 2 months later, and it can still recognize heartbeats. You do not even need to reprogram the Memristor, because if you program them the right way, they can be actually extremely stable. So yes, these are new results we are very excited about, but something I really want to insist in this presentation is that although we talk a lot about neural network, AI is not only about neural networks. In fact, neural networks excel at big data situations. So the idea of creating AI with neural network is that when you have really many examples, so for example, for image recognition tasks, you can download tons of images from the internet to train your neural network. And then you use all these mathematics of training neural networks, and you can train neural networks to do very complicated things. But in real life, not all the time we have access to big data. And especially for medical data tasks, which I believe to be so important, very often we don't have that much data, and the data we have very often is not very good quality. And in that context, neural networks do not behave well at all. So if you train neural network with small data that is low quality, what the neural network is going to do is just learn by heart the few data you presented. And if you present something that is even slightly different, the neural network will not be able to understand what it means. That's called overfitting, and that's a very big problem of neural network. So when you have small data, you really need to also rely on the expert knowledge, what people actually know about the data. And a very good way to do that is called Bayesian reasoning. So it's a type of AI that is much better for this small data situation, and that relies on Bayes' law that you might know. So basically, Bayes' law is the idea that if you want to know, so for example, if you make some observations on a patient and you want to know the probability that the patient has a given disease, this can be obtained by multiplying the probability that when a patient has this disease, we actually observe this observation, multiplied by the probability that a patient has this disease in general, not taking account the observations. And this is actually quite, when you have expert knowledge, it's actually quite easy to construct these things. They are very, you can combine everything you know about the disease to create this type of models. And so for medical tasks, that can be better adapted. Unfortunately, these things can really become hard to compute when you go in the mathematics of things. And so we also looked into how to accelerate this type of Bayesian reasoning with Memristors. So these are very new results, and they are going to be published very soon in a very prestigious journal. So I cannot really show you the details about how it works. It will be next seminar. But that's actually, I want to show it because that's the most complicated system we have fabricated with Memristors. And so this is a photography of the system. And this tiny square here, if you zoom onto it, you can see these arrays where the memristors are. And all around the memristors, you have actually CMOS transistors that do conventional operation. And the way the system works is that you have transistors around the memristors, and these transistors access only the memristors that are local. And so they do computation based on the memory that is local. And then when they're done with their computation, they can send it to the block that is next to them. And so that's why it's so energy efficient, is because, yes, you only need local information. You don't need to interrogate memory that is very far away. And this way you save a lot of energy. And so, for example, we have used these systems on a task of gesture recognition. And we have shown that this type of system would use 50 times less energy than a microcontroller unit, which is typically used for these small data AI tasks, due to all these efficient optimizations to make it energy efficient and using the nano device a lot more like an artificial synapse. So yes, crazy developments. And now so we are really happy with that, but we want to go further. And now I'm going to go on the side of our research that is really crazy. And for this, I want to insist that all these AIs that I showed before are pre-programmed. So the way it works is that basically you use a big computer to really optimize all the parameters of your AI. So that would be synaptic weight in the case of a neural network, or the likelihood and prior in the case of Bayesian model. And once you are happy with them, you actually program your chip with Memristors with the values of the parameters you found on the big computer. It would be really cool if you could actually do the training process with the memristors themselves. This way, the system can adapt to data, and also you can save a lot of energy, because I have mentioned before that creating AI consumes a lot of energy. But unfortunately, training AI with memristors is a very hard problem. Because the way we train AI is really bad. Because what I have told you before is that AI does not require very precise arithmetics. And so that's why we can use memristors. It's not true when you create the AI. It's only true when the AI is finished. Because when you create an AI, what you do is that you need to adjust your synaptic weight very finely. The way you do that is that you have your AI, and we have techniques that allow us to find the gradient of the parameter so that the AI becomes a little better. So what you do, you have an AI, you make this computation, and that tells you how you should change all your synaptic weights so that the AI becomes a little better. And you do that again and again and again and again and again and again. And at the end, you have an AI that is very powerful. But when you do that, it's really important that you are able to change your synaptic weight just a little. And if your synaptic weight is really the conductance of a memristor, that's actually problematic. Because I've told you, memristor, you change the synaptic weights by moving atoms in the memristors, literally moving atoms. And you have these filaments, and these filaments can be atoms diameter. So that's amazing. That's really nanotechnology that allows to do that. But that's not very accurate. That means each time you program Memristor, you do not get exactly the resistance that you want. And to do learning, you need very, very precise synaptic weights. So it's very complicated to do learning with Memristors. However, there is a solution that can work in some context, because there are other types to do learning in artificial intelligence. And one very interesting technique is called Metropolis-Hastings Markov chain Monte Carlo. So I think some of you might know it depending on what kind of engineering you are studying. But speaking in very rough terms, so the idea of Markov chain Monte Carlo is that basically you have a neural network, for example, with all of the synaptic weights. And what you do is that you change all the synaptic weights by a random amount, and you create a new model. And if your new model is good, you keep it. If it's not good, you discard it. And you repeat this process again and again and again. And at the end, you get a collection of models. So that's very, very rough terms. I think Aurelia is not happy with what I said, but it's just to give a very, very rough idea about how this works. And so when we do this type of MCMC, so it's not, so you don't really need to finally adjust the value of your synaptic weights. You need to recreate new values of the synaptic weights that are actually random. And here, as I told you, when you program Memristor, things are not precise. Actually, when you program a Memristor, the conductance you get is actually random. So maybe you see where I'm going. We have this algorithm that is very hard to do and that consumes a lot of energy, where you need to program the synaptic weights repeatedly, each time a random value. And Memristors, actually, each time you program them, you get a random conductance due to the imperfection of the Memristor. So that's why we realize maybe we can actually, so that's what you see here. You see, we program a Memristor many, many times, and we would want a Memristor to have 90 microsiemens. But in fact, you can see each time it's quite different. It follows a Gaussian law. So we are like, okay, to do MCMC, you need random numbers, and actually you need Gaussian random numbers. And when you program a Memristor, you actually get a conductance that follows a Gaussian law. So maybe we can actually use the imperfection of the Memristor, the fact that we actually don't control Memristors that well, to do MCMC with Memristors. And that sounded crazy, but that actually worked. So to go, so all the details are in our Nature Electronics paper, but I'm going to give very rough idea about how this works. So the idea is that we have an array of Memristors. So each of them is associated with a transistor. And each row of the array has all the synaptic weights of the model. And when you want to generate a new model, what you do is that you take the current that flows in one Memristor, and then you inject it onto the same Memristor in the same row. And this current will actually reprogram the new Memristors, but because the Memristors are imperfect, it's not going to end up in the same resistance as the previous resistance. It will follow a normal law that is based on the value of the resistance of the previous row. And so you get a new model, which is exactly what you would want to do MCMC. And we did that in practice, and we took a big array of Memristors, and using this technique, we have more than 16,000 Memristors, and we trained the neural network to recognize images of mammography, and the goal is to recognize mammographies that are fine and mammography that actually show cancer. And so this is all work that was done with our partners in Grenoble at Levy. And actually that worked really well. So this is a complicated slide, but I really wanted to show also real research so that you see how real data looks like. So what you see here is the value of the conductance of all the Memristors at the end of the learning process. So here you have the different columns that are the different synaptic weights of our model. And here you have the different rows that are basically, so we got 256 models. And you can see all of them are quite different. And if you look at distributions, they are quite complicated. And then you can, each of these rows is actually an independent model that can recognize cancer. And what is plotted here is, in green, is how good each of these rows recognizes cancer in percentage. So you can see some rows recognize cancer quite well, some others do not recognize cancer that well. And the first rows, I mean, it was really before learning really worked, so they are really bad. But what you can do is that you can take all these good rows and make some kind of majority vote to decide if the image is cancer or not. And if you do that, our system is actually able to recognize cancer 98% of the time. And that's really special because that's a new type of learning that is done exploiting the imperfection of Memristors. And we were really surprised it works so well. It works actually as well as purely software implementation. And also, because it's based on Memristor and in-memory computing, it uses very little energy. So we have actually not fabricated the full system, but we designed it and we estimated the whole system would use only 6 microjoules to learn to recognize cancer, whereas the computer would actually require 600 millijoules. So of course, we are still in a small task. We are not talking about gigawatt-hour, but our goal is, of course, to scale these systems to much bigger systems in the future. So yes, these are the conclusion of my talks. So I wanted to show that computing like the brain with nanoelectronic devices has huge potential to reinvent electronics. Challenge is to deal with device imperfection. Nanotechnology is imperfect, but actually here machine learning is very interesting because machine learning does not really need perfection. And even when you do, for example, the MCMC learning, imperfection can be exploited. Our next steps are really to scale these systems and really to go learning, because of course I showed you an application of recognizing cancer. So that seems very impressive because it's yeah, so important and difficult problem. But to be honest, this is really a simple version of recognizing cancer. So the task we did is hard, but it's not that hard. And so we need to be able to solve really hard tasks. But something also more general I want to say is that right now is really special times for research in electronics. Because, you know, for a very long time, we had Moore's law and you know, I mean, every year you get new electronics technology that is better and you get better transistors, and people really did electronics always the same way, and they would just update their design based on the new transistors that are available. Now it's not really the case anymore. Now, you know, we get newer transistors, but they are, you know, we reach like 3 nanometer technology. 3 nanometer technology is really hardly better than 5 nanometer technology. We don't have this same time of transistor progress than we used to. And also, machine learning has become so important, and machine learning has such this big problem of consuming so much energy. So it's really a time where we are really creative in electronics research. In the past, yeah, we did not have that much new ideas, but now we should really try new ideas all the time to solve these really important problems and without using new transistor. So that's why we developed Memristor. That's why we look at brain inspiration, really new creative ideas. And as a matter of fact, French government is very aware of that, and they understand that now times are really electronics has become so important. And I mean, we have seen all the drama during COVID when semiconductors were not widely available. And it's really important that we develop these new creative ideas so that France is well positioned on these new applications and becomes really independent in terms of electronics technology. So French government is funding this very big program that is more than 80 million euros to develop these very creative approaches to electronics. And this program is led by Isabelle Sang and Thomas Ernst at CNRS and CAR. And so this will fund research on new technology in electronics on all kinds of topics. So of course, bio-inspired computing, which is what I talked about, is in this program. And so we are really going to push a lot further the research that I have shown you in the PPR. But we also have projects on all types of electronics, including power, photonics, sensors. And for all these things, we actually have multiple master and PhD fellowships available. So if you want to do this type of PhD that really targets the future of electronics technology, please do not hesitate to contact me, and I will put you with the right people in touch that have these fellowships. We are hiring students right now. So I think I'm finished. I was really happy to give this talk, and I thank you for your attention.
Thank you very much, Damien. Very interesting talk. Do anyone have any question? Switch on my camera. Please do not hesitate if you have any question.
Maybe you can type the question if that's easier than.
Yes, we have one question.
Okay, so I'm trying to find my question.
Can you talk, or do you want to give your question in the chat?
Yes, I can talk.
Yeah, thank you.
Hello, Mr. Damien. Nice to have you. And I have heard your presentation with great enthusiasm. And I would like to emphasize this question. In the past years, we use, more improved transistors to make more dense electronic, like microcontroller and everything. But with the main resistor, right? Okay.
Yes.
What is the method we use right now? Can you come back on these points once more time? Thank you.
Yes. So you mean to really fabricate them?
Yeah.
So yeah, when you fabricate, so you do your transistors, and then you do wires. So this transistor is what is called the front end of electronics, and then you put layers on wires on top of your transistors to connect the transistors together. And what is really nice about Memristors is that actually where you put the Memristors. So you have what is called vias that connect the wires. And actually, at some locations, instead of putting a via, you put a Memristor. And this is deposited using a technique that is called atomic layer deposition. So that's really hardcore nanotechnology technique, because these Memristors need to be very thin. You see the one I showed, they are only 10 nanometers thick.
Yes.
It's very important that they are so thin, because when you program Memristor, you need to move atoms. So you need very high electric field. And the fact that they are very thin is what allows you to get very high electric field, even with a quite reasonable voltage. Because electric field is voltage divided by thickness.
Sure. Okay, thank you.
Okay, we have another question in the chat from Grégoire Sanso, who asks how long does it take to train a neural network with the process compared to the computer? So,
to be totally fair, we are actually not faster. And that's so as you may have not, so that's actually something that has really changed in electronics research. You may have noticed in my talk, I was like energy. I have never really talked about speed. When I was a PhD student, all we cared was speed. It was really speed. And energy was not that much of a concern. So, I mean, it was, but it was not that much the focus. So electronics has changed. I mean, neural networks are trained on GPUs, graphics cards, and they are actually extremely fast. And it takes a while to train a neural network, but it's not that big of a problem. On the other hand, energy is really money. It's, as I said, it can be millions of euros of electricity, and it's also a planet problem. So all the focus of electronics research has really kind of shifted to energy. And yes, so the training time is actually similar, but we want to be at least 1,000 times more energy efficient.
Do you have your answer?
The answer is similar. It's not.
Yeah, I know that, but I want to. I had quite the same question about MCMC, because MCMC is a very slow process. So, do you have in the computation time?
Yes. So MCMC is slow.
Yeah.
And we are not truly accelerating it. So to be totally honest, I think it's really exciting, but it will, I mean, pure MCMC will remain for this really small data task. At least currently, we do not know how to scale it. So if you can help, we are very interested. But what we are doing right now is to apply the same type of idea. So we use really that as concept work, and we apply it to Bayesian neural networks, which are neural network, but that keep some of the qualities of Bayesianism, of Bayesian approach, and in particular to behave a lot better on small data and to be able to estimate the confidence of the answers. And on MCMC, we kind of stopped here, but if you have ideas how to scale it, we are really interested.
Okay, we should talk. But I think there is someone else who has a question, so I will let. So I see Alkibiwot. I don't know what's your name exactly, but
my name is Albert.
Nice to meet you.
Hi, Albert.
Yeah, hi. It's a great presentation, actually. It's an eye-opener about this. I just wanted to understand something that you mentioned. You mentioned that in this Memristor project you've been working on, that the logic is closely placed next to the memory. I wanted to know how the logic, the memory and the logic share, like, for example, the microprocessor and the memory, the various memories placed in the different areas. How do they share the resource? Like in this case, maybe you have one microprocessor for the whole process, or like 4 microprocessors for the whole device. How do they share?
So in microprocessor, so you have different level of memory. So you have a main memory that is typically extremely far from the microprocessor, and that is extremely energy costly to access. And then you have cache memory that is much closer to the arithmetic, and that takes a lot less energy to access. And so a lot of microprocessor design is to try to access the main memory as little as possible, and to use this cache memory more and more because it's more energy efficient. And you have different levels of cache memory, and the higher levels are shared by all the processors, and the lower level is more specific to processor. And so when you do microprocessor, it's really important that memory is shared. And unfortunately, that really limits the energy efficiency, because accessing shared memory has to be costly, because if it's shared memory, yes, it has to be separate from where the computation happens. When you do AI accelerator, you are trying to do less shared memory, have memory that is more specific to some computation centers. And in the extreme type of research we do, the memory is not shared at all. It is super specific to a tiny processing unit. That's very extreme. And when you scale to bigger system, you may need to re-include some sharing. But that's really what research is about right now, to energy efficiency is no memory sharing, but applicability needs some sharing. So we need to kind of balance between the two. And that's a lot of our research in the field.
Sure, sure. Thank you.
Is there any other question? Oh, it's okay. So I think we should. Okay, so we have one question. One
Hello.
more question. Hello.
Yes. Thank you for this presentation. It was so interesting. Maybe basics question. In your research with RRAM.
So I'm sorry, I think your microphone, I think your connection is not that good. Maybe you can type your question.
Yes, that's everything.
I just could hear errors. No, absolutely no. So resistive RAM is my research. Actually, even I chose to focus this presentation on resistive RAM because I had only 40 minutes. But I also work on other type of technology, in particular spintronics, which is a type of devices that have magnetic aspect. So right now, so what is very hard to do is this type of really brain-inspired AI is very hard to do with transistors only. Due to the reason I told you, is that memory is hard to do with transistors. It's not impossible. I mean, people do it with transistors only, but it's quite limited. So usually this research involves other technology. Memristor is the example I showed here, but there are others. So in particular, there is a lot with magnetic devices. There are also people, and we do have that in our PEPR project, that do that with light, using photonics as actually tremendous potential for neuromorphic, because in photonics, you can really connect things in very interesting ways.
Thank you for your answer. You hear me now?
It's okay. Okay, thank you. Is there any other question? Okay, so we have another question from Mr. Akib Iftaker, and I think it will be the last question, because some of you have to go to. The recording video will be on the graduate school webpage.
Hello, can you hear me?
Yeah.
Yeah, so recently I was reading about the spintronics. So there is a professor from the Groningen University. I think he's working on it. He's the pioneer, I think. But still, the documents I went through it, they're saying that they're implementing it like from 2015 and in 2020 they are gonna bring it into the market. So I wanted to know, like, is it like, did they able to bring it? Because until now, like, I didn't see any kind of device which is using the spintronics particularly. It's still like most of the yes.
So twofold. So spintronics. So I chose not to talk about spintronics in this talk to focus it. So spintronics neuromorphic is really nice field. I'm actually working a lot with this, and we have the world specialist about this topic at the university, who is called Julie Grolier. So right now, spintronics neuromorphics tends to be more advanced topic than Memristor. So you don't have like this type of systems that I showed where you already have the Memristor integrated with transistors. We don't have that yet in neuromorphic spintronics, but it's happening. And actually, as a matter of fact, we are working on that right now. And I'm actually looking for a PhD student to work on this very precise topic. So spintronics is less advanced than Memristors, but it's actually more powerful than spintronics, than Memristors. You can do more sophisticated neurons and synapses with spintronics than with Memristors. About spintronics in general, I mean, spintronics is actually, so not for neuromorphic, spintronics is actually quite advanced technology when you use it as a normal memory, not as a neuromorphic memory. And actually, there are some products in the market that already use spintronics. So for example, one of the most expensive Fitbit device actually uses a spintronic memory called MRAM in its microcontroller unit. So the spintronics is actually quite mature, but not yet for neuromorphic.
Thank you.
Okay, I think it's time to thank you very much, Damien, and to thank everyone